me. This is some work that I've been doing with collaborators who, when we started this work, were all at Glasgow: Konstantinos Ageropoulos, Suchi Chow, and Jill Stewart. Suchi is now in China, and I'm now split between Glasgow and Cardiff University. And what I want to do here is talk you through this piece of work in a kind of, to give you an overview at the beginning, but then I want to talk in more detail about how we've done the modeling of what I'll loosely call human behavior, since that's what we're all interested in here. So I'm not going to focus too much on the empirical stuff. I'm going to focus on the modeling, which is the mathematical modeling, which is an economic model. My first language isn't economics. I hope that I will be somewhere in the space between trying to understand this myself and trying to communicate it that will make sense to you. Apologies in advance if I fail on that. But let's get started. Okay, so what are we interested in? We're interested in here the mortality transition, or the epidemiological transition. And that's the monumental decline in mortality that occurred in industrialized economies during the latter half of the 1800s and the first half of the 1900s. And you can see here on these plots, we've just plotted the crude death rate in England and Wales, Scotland, London, and Glasgow. And you can see that over this period between 1840 or 1850 and 1960, we see this massive decline in the mortality rate. And what I want you to notice here is that it's a big decline, that it's S-shaped, and it's not exactly the same in all those areas. And it's important because it catalyzed improved welfare and economic growth for the following century at least. And in the literature, there's a lot of work on the drivers of this monotonic decline, including what it was that kind of drove this, health improving technologies, improvements in living conditions, and people have tried to understand what drove it. But actually, there's much less work on what those dynamics look like. So what we do here is we model health technology adoption behavior, and we try to explain both that sigmoid shape of the dynamics and the differences in timing of fast declines. And I'm decided that I'm going to refuse to let Copilot steal "this matters" from me as an expression and say these things matter because inequalities in the timing of accessing the benefits are important for populations at the time, but they're also really important because they generate long-term health and socioeconomic inequalities. So in terms of, just to link this to the themes of the workshop, it's not a single epidemic I'm focusing on here because this is the current piece of work that I'm doing that has behavioral stuff in it in the most obvious way. This is sort of the sum of all of the epidemics that happened and the results of the reductions in mortality driven by a range of factors. So something slightly odd going on with the ordering of the slides. Okay, so what do we do? Well, we started off by looking for what economists call stylized facts in the data, this S-shaped decline, etc. But how do we get those data in the first place? So using historical archives and maps, we compiled a novel data set, and I say we, this is primarily Jill and Suchi, who did a lot of work on this. It was a lot of work. Looking at maps, looking at how they mapped onto one another, how areas fitted together, trying to find data sets that could actually be combined and continued over a long period of time from the archives. So they've compiled annual mortality rates for the city level and for the small constituent areas that we can call divisions. Some of them are parishes, some of them are metropolitan boroughs, etc. By combining data from different sources. And they've also collected data on socioeconomic conditions close to the start of the period of the decline and some additional control variables. And we think it's a major contribution really to be able to trace these small areas and thus those inequalities over such a long period of time. Sorry, I shouldn't have changed slides. So what I'm showing is just a snapshot of 2 bits of the data for London. So this is crude mortality by division in 1860. So you can see there are areas that have higher mortality than others. And this is the percentage of the population, or at least the males in the population, who are professionals divided by industrial classes. So it gives you an idea of the kind of socioeconomic conditions in the areas, in the divisions. Why are we back on that slide? I don't know. Okay, maybe I'm pressing the wrong button. So when we look at those data in a bit more detail, so now the time series for those divisions, what we see is differences between them. So this is just a few illustrative examples. We see the S-shaped decline reasonably well in most of the areas, nonetheless. And we've fitted here a logistic curve to those mortality data. And what we've plotted here in blue circles are the inflection point of those curves. And what I think I want you to notice is that there are differences in the timing of the fastest declines, that is, of the inflection point between these areas. And by and large, if we look at the top row, which we can think of as the kind of better areas in some intuitive way, we see that the inflection point comes earlier. They're benefiting from whatever that technological progress was in health improving technologies earlier than those on the bottom row. So what we wanted to do in the first step was just make sure that that was borne out when we ran some statistical analysis. So I'm not going to talk you through the detail of this at all because I want to get onto the behavioral modeling, but just to say that we extended the logistic model to include to make each parameter a function of the socioeconomic conditions at the start of the period to see what extent that was driving things. And what I want you to focus on is this key parameter, gamma tau C, which will tell us whether the inflection point comes earlier or later. So what we observe what we find when we run this model, estimate the model, is that robustly the inflection point is seen earlier in divisions that have a higher proportion of high income individuals. And that works out whether we look at the percentage professional over percentage industrial or various different measures of socioeconomic conditions and at different points in time, but also for infant mortality, non-infant mortality in London and in Glasgow, etc. So what we saw intuitively in the pictures is borne out statistically. So our 2 empirical observations are that mortality declines were sigmoid, S-shaped, and the timing differed between areas with high and low proportions of high-income individuals. So naively, we might say, okay, if we wanted to reproduce those sigmoid mortality dynamics, we could assume that whatever health improving technology existed, it progressed in a sigmoid way. But unfortunately, that wouldn't explain the differences between the areas. So here what we're going to do is propose an explanation that can explain both observations. And to do that, we develop an economic model, and it's intentionally stylized. I don't know if it will look stylized and simple here. I don't know what kind of reaction you'll have to it. But relative to other models that I'm working on with these collaborators, it's quite straightforward. But this allows us to obtain analytical results. But also our data is not, I mean, it's a decent sized data set. For historical data, it's pretty good, but we don't have a lot of detail. So we need to make sure that we only have parameters in our models that we can actually calibrate and do something useful with. So the model has these ingredients. Maybe to start, the decision that's made by the agents, and if you like, their behavior, their decision, their choice, and I'm going to use those terms interchangeably. I know they're used differently by different people in different disciplines. I'm going to be slippery with them. The decision made by agents is that of whether or not to adopt the health improving technologies. So they have this binary decision to make it at the point in time. So this economic model has the following ingredients. It's got a survival function, S, which tells us the rate, or at the individual level, the probability of survival, and this is 1 minus mortality rate, as a function of the health technology that's available and the individual decision or not to adopt. It has in it the resource constraint, or the budget constraint, which I think we heard a little bit about mentioned yesterday. And that captures how an individual partitions their income between consumption and health improving technology adoption that is in effect in this model, the investment decision. It has in it the expected lifetime utility, U, which is the quantity that individuals want to maximize. And as a result of that, we can derive a decision rule for the agents, for the individuals, which we call G, and that's the function that governs individual behavior, that governs those decisions. What we want to care about in order to compare with the data about mortality is the aggregate level, and we call that the adoption rate, if you like, F. That's the aggregate level behavior. So I'm going to talk through those things in turn now. To hopefully explain what's going on. So the survival function S shows how survival is improved by adopting health improving technology. So we can write it analytically kind of like this, but maybe what an easier way to think about it is to look at a specific example. So this is just an example. So you start off with baseline survival theta at the beginning of time, effectively, the maximum mortality rate. If you adopt the health improving technology, then you get a survival advantage, HK. But in order to do that, so you need to pay a cost, psi k. This is the indicator function that tells you whether you've chosen to do that or not. So obviously adopting health improving technology has benefits for you as an individual, but it also has costs. And that's captured by the resource constraint or the budget constraint. So what do we have here? We have the income of the individual YI, and that's split between the consumption part. That's all the stuff that I do that I want to do is spend my money on. And the bit to do with adopting the technology. So if I choose to adopt the technology with the indicator function of the cost, and I multiply that by the cost, that's the investment. So I partition my income between consumption and, if I adopt, the cost of adoption. And what might that represent? It might be the additional rent that you pay to live in a property that's connected to the fresh water supply, just to give an example. Now, that's all very well, but how does an individual actually decide how they're going to make that decision? How are they going to adopt or not? So, as a standard assumption in economics, individuals seek to maximize their expected lifetime utility, and that allows them to do that trade. So we model that as UK, the expected lifetime utility from the UK onwards, and it's the sum of the utilities that you get from your consumption, UCI, discounted in each period by the discount factor and whether you've survived. And because we've set it up that way, that's a geometric series, and so we can compute the sum. Doesn't matter too much what this looks like, but it's possible to get an analytic solution in this particular case. So what does this model assume? It's that consumption has utility benefits. I care about it. It matters to me. And the benefit of adopting the health improving technology in this particular model, you don't get direct benefits from that, but you live longer. And so you can enjoy those benefits for longer. So you get more of them over your lifetime. Okay, so since we only have the choice to make of whether we adopt or not, the individual problem looks quite straightforward in a sense, because it's now, we can say, okay, so in the previous slide, we had that expression on the right-hand side. I said, don't worry too much about the form of it, but we see it comes up twice in this equation here, G, the individual problem. So this is the utility, the expected lifetime utility if I adopt, because I have to pay the cost psi k. And this is my expected lifetime utility if I don't adopt. I don't have psi k. It's basically just the same as the expression on the right hand side. As we go back, this one here on the right hand side. Right, that's going back. Okay, so what we care about now is that if I'm going to adopt, I need this thing to be bigger than this thing. The utility that I get over my lifetime is going to be higher if I adopt than if I don't adopt. Otherwise, I don't adopt. So we can show analytically that there's a threshold level of income Y star. See the Y in here, but the Y star, above which an individual will choose to adopt. And we can also show that this threshold reduces as the benefits of the health improving technology HK increase. So if I get more benefit from that health improving technology, then the threshold comes down and I'll opt in earlier at a lower income. Or as the cost of accessing psi k declines. So as technology, health improving technology gets cheaper, I'm more likely to opt in. So put another way, my behavior is given by the relationship between my income Y, I, and the income threshold Y star, which in turn depends on HK, the improvement I get from the health improving technology, and psi k, the cost. Okay, so that was all the individual stuff. How do we sum all this up to the aggregate level? So the function governing aggregate level behavior we call F. What we really care about is this in a sense, because that's what our data on mortality are telling us. At the aggregate level, this adoption rate F is the proportion of individuals who have income above the threshold. And that's based on the income distribution. So if we think of this, so this is the income distribution. If you'll excuse that Y is on the x-axis, that's the income. Then if this is the income distribution, and that's a kind of typical sort of shape for an income distribution, then what happens is that we pick up as we move this way. These individuals here are opting in. The individuals with these incomes here are not opting in. So the proportion of individuals who are opting in is 1 minus the CDF of this. So this is the PDF of the income distribution. We can think of those individuals who opt in as 1 minus the CDF here. So we can easily work out, if you like, what proportion of individuals opt in. So importantly, there's Y star. So are we done? It's kind of the question. Not quite. Importantly, Y star depends on the cost of adoption psi k. Now, we don't have any information about psi k. We don't really know how much it costs individuals to benefit from these technologies. So one solution might be to impose a process for it, and we would then be treating this psi k as exogenous. We say, for example, technology gets cheaper over time, and solve the problem as what economists call the partial equilibrium problem. But if we do that, then we have to assume an ad hoc process for psi k, which we don't know, and the individuals decide independently of one another whether to adopt. So what we'd prefer to do is make an economically grounded, more general assumption about how psi k responds to the demand and technology. And this creates a feedback in the system, and it means that we have to solve for what we call the general equilibrium solution. So the logic here is that as more individuals adopt the technology becomes cheaper per individual. And we'd expect that to be the case here because we get economies of scale. So, for example, some of the major technologies over this period were fresh water and sewerage provision, and we'd expect those to be less expensive per individual to connect to once the main infrastructure is in place. And once the infrastructure to connect people is there and the people who are doing that connection exist and are well trained. So we assume that the cost, psi-k, is a negative function of the proportion of individuals who adopt, the adoption rate F. And we can write that down as we see on the slide. And all of this implies that psi-k is endogenous. It's not fixed by us from the outside. In each period, the proportion of people who adopt, which is determined by Y star, the income threshold, and the cost psi-k are jointly determined. And to solve for that, therefore we need to solve for the value of psi-k as well, the general equilibrium in each period. So when I use the term equilibrium, partial and general equilibrium here, it's not in relation to the start and end points of the S shape, it's in relation to whether we have this feedback or not in the system. So we show analytically that the general equilibrium solution to this problem exists and is unique. So when we get a solution computationally, we know that we've got the only solution, not one of hundreds of possibles. And then to solve it, we use a fixed point algorithm. There are two predictions of the model in general that we can derive analytically. And they're basically what we cared about in the first. So prediction 1, given the approximately log normal distribution of income over the period, so this shape here, which is quite classic for income, the model predicts that we should observe a sigmoid pattern in mortality as Y star reduces, without further assumptions regarding how the health improving technology actually works. So what this shows is that as you move Y star K, the threshold to the left, that is, the income threshold is falling because the cost is falling for some reason. We pick up more and more individuals. And you can see that if you were to plot the CGF of that curve, you would get the S shape, the sigmoid pattern. Prediction 2, areas that have a higher proportion of high income individuals should see an earlier decline in mortality. So in our top figure in A, we have a distribution of income that has more high income individuals in it. And we can see that we start picking them up much earlier, or we pick up more of them earlier than if we take the same figure for an area that has higher income inequality and fewer individuals with high incomes. So as we pick things up here, we see that the proportion of individuals who are adopting takes longer to take off. And the proportion of individuals adopting directly affects our mortality rate. So that's how it translates into the mortality rates. We can show all of that analytically by taking derivatives and looking at the convexity of the curves. So how do we then take this to the data? We calibrate the model using new data on the full income distribution. So this is quite rare. We have rental values at different points in time for pretty well all of the properties in Glasgow. And that allows us to see what shape that income distribution curve has, kind of proxy for consumption. We use standard values for the discount factor beta, that's all sort of standard economic stuff, and a standard logarithmic utility function, although we could change that if we wanted to. And we try to make reasonable assumptions about the functional form of the response of per unit cost psi, the cost of adopting, as a response to demand, i.e. as a response to the proportion, that's something else, the proportion of people who opt in. So we might say it's a proportional decline. We just say it's proportional to the number of people who have adopted the reduction in cost. And then we want to explore assumptions about the time path of HK. So how much We can explore how much that matters. And all of this allows us to solve the model quantitatively. So, for example, when we put the actual distributions of income into this, do we generate the sigmoid pattern? Now, I wanted to explain all of that background stuff, so I'm not going to show you very much in terms of results. This is just an illustrative computational solution to this problem, just to show you kind of that we can do it. We're still working on this. This is still work in progress. It's not intended to be a kind of results in any formal sense. So these are our income distributions over time. So you can see that the income distribution actually spreads out as we come through time. And so the income inequality is worse at the start than it is at the end of the period. You can also see that the income increases. But what I want to show you here is that our kind of headline measure, the mortality rate declines that we wanted to observe in the first place, we do indeed generate this sigmoid pattern. And we do that even when we assume that there was no improvement in health technology at all. So we can generate this simply from the shape of the income distribution curve. Of course, it's not quite that simple because we don't actually reduce far enough here in terms of the mortality rate relative to the data. So we're going to play with this a bit more to try and see what we can do to be more confident about these as results as opposed to as an illustration. But what we have shown is that you can generate this shape without having to impose a particular functional form on the shape of H, the progress in health technology. So once we've calibrated the model, we've kind of half done it, and we'll try and do it a bit better. What can we do with it? So we're hoping to try out some counterfactual experiments. For example, we can ask how the dynamics of the mortality rate might change as a result of different assumptions about the process of health improving technology. So it might be that it has faster or slower improvement, or that all the improvements take place at the beginning of time rather than later on, or so this helps us to understand the effectiveness of health improving technologies and their impact on the mortality rate dynamics. So this is a kind of question to do with, might help us understand something about the epidemiology, but also the public health of the period. If we assume that, so if we take another experiment, if we assume that the income distribution changed differently over time, if inequality increased or decreased, we can explore the impacts of income inequality on how these technological changes become adopted and the effects that they have. And it might be that so we might say, okay, well, our counterfactual experiment here corresponds to somewhere else in the world at a different period of time or for a different technological change. And we can also explore the dependence of the per unit cost of adoption of the health technology on the adoption rate. So we might say, okay, at the moment, I think we've got it's proportional to the number of people, 1 minus the number of people who've adopted. But we could change that assumption as well and see how big an effect that has and what kind of changes we need to make to better fit the data, or once we've better fitted the mortality data, better match the mortality data, what impact those changes have. The left button's going forward and the right button's going back. It's very odd. Anyway, okay, so we're still back on that slide. I was trying to get back to conclusions now. No, that's down and that's going up the way. What? Okay, there we go. Okay, and then I pressed the same button and it went the other way. very old. Anyway, okay, so we've shown that mortality reductions followed sigmoid dynamics at different spatial scales at the city level and pretty well at most of those division levels. The period of fastest declines occurs earlier in areas with a larger share of higher income residents. It's much clearer than for those with the greatest scope for improvement, which could have been how it worked out. We've developed a stylized economic model that produces sigmoid mortality dynamics without strong assumptions on the dynamics or convexity of HK, the progress in health technology. It produces earlier declines in mortality in areas with a higher proportion of high-income individuals, as we hoped. It generates realistic mortality dynamics when calibrated and solved computationally, not exact, but kind of realistic-ish. And it allows us to carry out counterfactual experiments to explore the effects of alternative scenarios for the dynamics of the health improving technology, the income distribution, and the dependence of the cost on the adoption rate. So that's kind of what we've achieved thus far with this. Just want to say thank you for the funding that we've had to do this work. And I think I hope I've sort of shown you a little bit that using historical data can allow us to ask and answer some interesting questions. I just want to point out too that using historical data can be a great way to have new data for student projects. And so, yeah, if anyone wants to talk to me about that, that would be great too. Thank you very much.